Hello and welcome back to this channel once again. Now in this lesson, we are going to learn how to solve linear differential equations using the differential operator method, which is the D operator method. Now in this lesson, we are going to focus on first order linear differential equations, and then we consider second order linear differential equations in the subsequent lessons. Before we get into this lesson, let's familiarize ourselves with certain or some common D operator notations we may come across. So let's assume that we have a function y, which is a function of x. Now if you want to find the first derivative of this function, then you have dy dx. We call this the first derivative of y with respect to x. If you want to find the second derivative, you have the square y over the x square. This is called the second derivative. If you want to find the third derivative, then you have the cube y over the x cube. Now, how do we represent this in the D operator form? So, for the first derivative in the D operator form, you have capital D times y, that is the first derivative. And then if you want to find the second derivative, that is represented by the square y. The third derivative is represented by the cube y, and so on and so forth. Now, generally, if you have d to the power n divided by d times x to the power n, then that is represented in the D operator form as d, or capital D, to the power n. So generally, this is the formula we use to represent dy dx, or the squared y over the x squared, and so on and so forth, in the D operator form. Now let's try some examples. Let's consider some examples to see how the D operator also works. So assuming that we have, let's say, the square of the function 3x squared. Now what this primarily means is that we are going to perform the operation on the function 3x squared, and thus we are going to differentiate 3x squared twice. Now when you differentiate 3x squared once, you have 6x. When you differentiate it again, then you have 6. So the square into brackets 3x squared is equal to 6. Again, if you have d cos x, then that is equal to, you differentiate cos x once, and then you have negative sine x. Again, assuming that you have 1 over d times the function x, or 1 over d of the function x, we know that the inverse of differentiation is integration. So you want to integrate this function, so you have the integral of x dx, and that is equal to, you increase the exponent by 1, and then you divide by the total exponent, plus c, which is the constant of integration. So here the power is 1, so you increase by 1, so that becomes 2, and then you have divided by 2. So basically this is how the D operator works. Now let's consider some fundamental properties of the D operator. So the first one we are going to talk about is the distributive property. So if you have d to the power n into brackets u plus v, then basically you are going to distribute d to the power n across, so that you have d to the power n times u plus d to the power n times v. So basically we are distributing d to the power n across. B, if you have d to the power n of k times u, where k is a constant, then basically you are going to pull out k, and then you have dn, or d to the power n of u. And then c, we are going to talk about the index law. So if you have d to the power m times d to the power n of u, then this becomes d to the power m plus n, because we have same base, and then because we have same base, we can add the exponents, and then you have, so you have d to the power m plus n of u. So basically these are some fundamental properties of the D operator. Now let's consider a first order linear differential equation, which is given of the form y prime minus ay equals g of x. Now we can represent this in the d operator form. So y prime is dy dx, and that is equal to capital D times y minus ay equals g of x. Now we can factor out y, which is the common term. So we have d minus a, and then you have y on the right equals g of x. Now we can divide through by d minus a, so that we have y equals 1 over d minus a times the function g of x. Now, so long as we can represent the given differential equation in this form, then it means that we can have y to be equal to e to the power a times x times the integral of e to the power negative ax times the function g of x dx. Now, this is the general formula, or this is the formula to find the general solution to the given differential equation. The formula to find the general solution to the given differential equation. So, assuming that we have an example, we want to solve the differential equation d minus 2 times y equals e to the power x. Now, notice that with this, we can multiply y across so that we have dy minus 2y equals e to the power x, and then we know dy is y prime, and then minus 2y equals e to the power x. So actually you can represent this differential equation, the differential equation given, from the d operator form back to the normal or the usual notation we already know. So given this differential equation, let's try to find the general solution using the d operator approach. Now, to solve this differential equation, first we have d minus 2 all times y equals e to the power x. Now we divide through by d minus 2, and then we have y equals 1 over d minus 2 times the function e to the power x. Now, so long as we can represent the differential equation in this form, then using this formula we can find the general solution. So we have that equals to e to the power. Now, considering this formula, here we have 1 over d minus a. This is a negative value, but you have a positive value here. So once this is negative, we have negative 2, then this becomes plus 2. So we have e to the power 2x times the integral of e to the power. This time we have negative, like what we have here. So that becomes negative 2x times g of x. Now we have g of x to be the function on the right hand side, which is e to the power x, and then times dx. So we have this to be negative a, which is negative 2, and then on the outside we have e to the power a, which is a positive value. So negative 2 becomes positive here, so 2x, and then we have the integral of e to the power negative a, so negative 2x times g of x, which is e to the power x, and then dx. So let's try to work out this. So we are going to have on the outside e to the power 2x times the integral of e to the power. Now here we have negative 2x plus x, and that becomes negative x. So we have e to the power negative x dx. Now let's try to integrate e to the power negative x. So that becomes e to the power negative x, and then we differentiate the exponent, which is negative x, with respect to x, and we have negative 1. So negative 1 appears at the denominator. So we can essentially represent this as negative e to the power negative x, and then plus the constant of integration. Therefore we have e to the power 2x times negative e to the power negative x. So usually we can simplify this as negative e to the power 2x minus x, that is to the power x, and then plus c e to the power 2x. Now let's make this constant c1, okay, and this one also c1. Therefore, we have c1 e to the power 2x minus e to the power x. We call this the general solution to the differential equation given. This is the general solution. Now, aside from this approach, we can use a shortcut method to find the general solution as well. So let's try the shortcut method together. So, given the differential equation, that is the same differential equation, d minus 2 times y equals e to the power x. Now, to solve this differential equation, we are going to consider the first case. So, for case 1, when we have g of x to be an exponential function of the form e to the power ax, then we can represent the particular solution as 1 over f of d, where f of d is said to be the polynomial function of the d operator, times e to the power ax. Now, we can further represent this as 1 over, now here we are going to substitute the value of a in the polynomial function. So we have f of a times e to the power ax. And then this approach or this formula is going to be valid so long as f of a is not equal to 0. So long as f of a is not equal to 0. Now, in the case this approach fails, that is if f of a is equal to 0, then what you are going to do is, that is if f of a is equal to 0, then we have yp equals, you are going to multiply the numerator by x, so you have x times 1 over, and then for the denominator, instead of f of d, this time you have f prime of d. So you are going to differentiate the polynomial function of the d operator, that is, you are going to have the first derivative and then times e to the power ax. So we further represent this as x over f prime of a, we are going to substitute a in here, times e to the power ax. This is also valid so long as f prime of a is not equal to 0. Now, in the case this also fails, it means that this is going to be x squared and this is going to be f prime prime, and so on and so forth. Now, given this differential equation, notice that this shortcut approach only finds or only solves for the particular solution. Okay, so given this question, first of all, you need to find the complementary function, and then we use the shortcut method to find the particular solution, and then we add the two solutions. So if you want to find the general solution, we have d minus 2, and then usually you are supposed to find the corresponding homogeneous differential equation, and then you find the complementary function. So for the complementary function, you have the auxiliary equation m minus 2 equals 0, and then you have m equals 2. Now, since you have m equals 2, it follows that yc is equal to c1 e to the power 2x. So this is the complementary function. Now let's move on to the particular integral or the particular solution. Therefore, you have yp equals 1 over f of d times e to the power ax, and this is equal to 1 over, now f of d here is d minus 2, so we have d minus 2 times the function g of x, in this case is e to the power x. Now the coefficient of x here is 1, so we have e to the power 1 x. Now we are going to substitute the value of a in here, so that is 1. So this is going to be 1 over 1 minus 2 times e to the power x, and that is equal to 1 over negative 1 times e to the power x. So finally we have negative e to the power x. So we have yp to be equal to negative e to the power x. So this is yp, this is the particular integral. Therefore we have the general solution given as yc plus yp, and that is equal to yc is c1 e to the power 2x, and then plus, so minus e to the power x. So this is the general solution to the differential equation given. So comparing this to the initial one, you realize that we have the same solution. So one thing you need to take notice of is the fact that the form of g of x determines the solution process you are going to use. So if you have g of x in this case to be an exponential function, then the solution process is going to be slightly different from when you have a sine or a cosine function, or when you have a polynomial function, or when you have the sum of two functions or the product of two functions. Now in the next section, we are going to solve examples to cater for all the other cases. So let's move on to the second example. So for example 2, this time we have a linear differential equation where the function g of x is equal to either a sine or a cosine function. So how do we solve such differential equation? Using the d operator method. So we are given the differential equation 2d minus 3 all in the bracket times y equals sine x. Now you know the first thing we need to find is the complementary function. So given this differential equation, we can have the auxiliary equation. Let's say we have 2m minus 3, and that is equal to 0, so that we have 2m equals 3. We divide through by 2, and then we have m equals 3 over 2. Therefore, we can say that yc is equal to c1 e to the power 3 over 2x. So this is yc. Now let's move on to find yp, which is the particular integral. Now we have the differential equation 2d minus 3 all times y equals sine x. So we can represent this differential equation in the form y equals 1 over 2d minus 3 times sine x. Now the moment you have either a sine or a cosine function, then the solution process changes. So if you have yp equals 1 over f of d times g of x, okay, where g of x is either a sine function, that is sine ax plus b, or a cosine function cos ax plus b, then what this primarily means is that you are going to put either d square equals negative a square, or the cube equals d square, which is equal to d times negative a square, or better still, you can have d to the power 4 equals negative a square, and that is equal to a to the power 4. So you may put either of the following into the particular solution. Now here we have yp equals 1 over 2d minus 3 times sine x. You realize that we don't have any equation for d, so the best thing we can do here is to multiply top and bottom by 2d plus 3, which is, we rationalize this by multiplying top and bottom by the conjugate of the denominator. So we are going to have yp equals 2d plus 3 over 2d plus 3 times 1 over 2d minus 3 times sine x. So let's simplify this. We try to expand and then simplify. So at the numerator, we are going to have 2d plus 3 divided by, now 2d times 2d, we have 4d squared, and then 2d times negative 3 plus 3 times 2d goes to 0. We have 3 times negative 3, that is giving us negative 9, and then we have times sine x. Now here we have d squared at the denominator, and then we know d squared is equal to negative a squared. Now looking at the coefficient of x here, the coefficient of x here is a. and then here we have the coefficient of x to be 1. Therefore, we have our a to be 1. Therefore, we have d square to be equal to negative 1 square, which is equal to negative 1. Therefore, we put negative 1 here at the denominator. We have 2d plus 3 over. So we are going to have 4 times negative 1, that is negative 4. So that becomes negative 4 minus 9. Let's simplify this as negative 13, and then times sine x. Now let's simplify further. So we are going to multiply sine x across at the numerator. So we are going to have 2d sine x plus 3 sine x, all divided by negative 13. Now here we are going to have 2 times the first derivative of sine x. We have d sine x. Now when you differentiate sine x, you have cos x. So that becomes 2 times cos x plus 3 sine x, all divided by negative 13. Therefore, we have yp to be equal to negative because of the denominator we have here, which is a negative value. So negative 2 over 13 times cos x, and then minus 3 over 13 sine x. So this is the particular integral. Therefore, the general solution to the differential equation given, which is y is equal to, we have the complementary function, which is c1 e to the power 3 over 2x, and then plus the particular integral. So we have negative 2 over 13 cos x, and then minus 3 over 13 sine x. So this is the general solution to the given differential equation. Let's consider the next example. So again, let's consider an example where we have g of x to be either a sine or a cosine function. Let's try to solve this example together. So here, straight away, let's find the auxiliary equation. From this, we have 3m plus 2 equals 0. We have 3m equals negative 2. We divide through by 3. And then we have m to be equal to negative 2 over 3. Therefore, we have yc, the complementary function, equals c1 e to the power negative 2 over 3, negative 2 over 3 x. Now let's try to find the particular integral. So for this differential equation given, that is 3d plus 2 in a bracket times y equals cos 2 over 3 x, we can represent this as y equals 1 over 3d plus 2 times cos 2 over 3 times x. Now, we said in the previous example, in example 2, that when you have yp equals 1 over f of d times g of x, where g of x is either a sine or a cosine function, or cos, let's say, ax plus b, then we are going to put the square equals negative a square and so on and so forth. Now, in the previous example, I forgot to make you know that if this equation fails, let's say you have f of d to be equal to 0, then you need to introduce the next one, which is yp equals, this time you multiply the numerator by x, so you have x times 1 at the numerator, and then at the denominator, instead of having f of d, you are going to have f prime of d, and then you work with that one. If this one also fails, then you move on to x squared over f prime prime of d, and so on and so forth. So let's focus on the first equation. So here we have the denominator to be 3d plus 2. Since we don't have d squared, or d cube, and so on and so forth, we are going to rationalize this function. So we are going to multiply top and bottom by the conjugate of the denominator. So we are going to have yp equals, we have 3d minus 2 over 3d minus 2 times 1. So let's say times 1 cos 2 over 3x, all divided by 3d plus 2. So let's multiply across. So at the numerator, we are going to have 3d minus 2 all times cos 2 over 3x, all divided by 3d times 3d, we have 9d squared, 3d times 2 plus negative 2 times 3d, cancel out, and then we have negative 2 times 2, which is negative 4. Now we know that the square is equal to negative a square, and then we have a to be the coefficient of x. Okay, the coefficient of x. Now the coefficient of x here is 2 over 3, so that is negative 2 over 3 square. That becomes negative 2 square is 4, 3 square is 9, so that becomes negative 4 over 9. So here we are going to have this to be equal to 3d minus 2 all times cos 2 over 3x, all divided by, we have 9 times d square, negative 4 over 9 minus 4. Now here we have 9 cancelling out 9, we are left with negative 4 minus 4. So this is equal to 3d minus 2 times cos 2 over 3x, all divided by negative 8. Now let's work on the numerator. So we multiply cos 2 over 3x across. So we are going to have 3d cos 2 over 3x minus 2 cos 2 over 3x, all divided by negative 8. So that's going to be, we are going to have 3 on the outside. Now you are going to differentiate cos 2 over 3x once. This is the first derivative. So when you differentiate cos, you have negative sign. So we are going to have negative. So first you differentiate 2 over 3x with respect to x, and then you have 2 over 3. Because you are differentiating cos, you have negative sign. So negative, and then we have sine of 2 over 3x, and then minus 2 cos 2 over 3x, all divided by negative 8. Now 3 cancels out 3, and then we are left with negative 2 sine 2 over 3x minus 2 cos 2 over 3x. Now negative 2 goes here once, so here becomes plus 1. Negative 2 goes here once, it becomes plus 1. Negative 2 goes here 4 times, it becomes plus 4. Therefore we have yp to be equal to 1 over 4 sine 2 over 3x plus 1 over 4 cos 2 over 3x. So this is yp. Therefore the general solution y is given by yc, which is c1 e to the power negative 2 over 3x plus yp, which is plus 1 over 4 sine 2 over 3x plus 1 over 4 cos 2 over 3x. So for example 4, this time we have g of x to be the sum of two functions. So how do we solve this type of differential equation? So let's do that together. So straight away, let's find yc. So we have m plus 2 equals 0. We have m equals negative 2. Therefore, we have yc to be equal to c1 e to the power negative 2x. This is yc. Now let's move on to the particular integral. So here we have y equals, that's we are making y the subject. We have 1 over d plus 2 all times x squared minus e to the power negative 2x. Now here we have the sum of two functions. We have x squared to be a polynomial function, and then we have negative, or let's say we have e to the power negative 2x also to be an exponential function. Now if you are solving for a polynomial function, the solution process is different. If you are solving for an exponential function too, the solution process is quite different. So to find the particular integral, what you are going to do is to consider each function at a time. At the end, we add up to get the particular solution, the original particular solution. So first of all, let's say that for yp1, now for yp1 we are going to consider the polynomial function, which is x squared. So that is 1 over d plus 2 times x squared. Now whenever you have a polynomial function of degree n such that n is a positive integer, then we should be looking out for one of these two expansions. So let's say you have 1 over 1 plus d, then you should be looking out for the expansion. So 1 over 1 plus d is equal to the expansion 1 minus d plus d squared minus d cubed, and so on and so forth. And with this, you need to use the binomial expansion. Okay, the binomial expansion. And then let's say if you have 1 over 1 minus d, then that should be equal to, you have 1 plus d squared plus d cubed, and so on and so forth. So you should know the expansion for 1 over 1 plus d and then 1 over 1 minus d. Good. Now aside from this, we are going to make sure that we represent this, that is the denominator, as one of these two. So here we have d plus 2. Now if you have d plus 2, we can factor out 2. Okay, so usually you want to target the term with the lowest degree. Now if we factor out 2, then we are going to get something like d over 2 plus 2 over 2, which is 1. And then we basically interchange the positions of these two terms so that we have 1 plus d over 2. So that is how we are going to manipulate the denominator. So this will be equal to, we have 1 over 2 on the outside, and then into brackets 1 plus d over 2 times x squared. So therefore we have yp1 equals, now using this expansion, we are going to have 1 over 2 on the outside. So 1 over 2 on the outside, and then using this expansion, we have 1 minus, now in place of d here, we have d over 2. So 1 minus, we have d over 2, and then plus d squared, so d over 2 square. Now the degree on the polynomial gives you the number of terms you are supposed to expand to. So since we have x to the power 2, then we are going to end at this to the power 2. So, and then all times x squared. Now let's solve further. So we have 1 over 2 into bracket, we have 1 minus, this becomes d over 2 plus, we have d squared over 2 squared is 4 times x squared. So we are going to have 1 over 2 on the outside, and then x squared times 1 is x squared minus x squared times d over 2, that becomes dx squared over 2, and then here we have d square x square over 4. So let's simplify this. So we have 1 over 2 times into bracket x square minus. Now this means that you want to differentiate x square once. So when you differentiate x square once, you have 2x. So 2x over 2 plus the square x square means that you want to differentiate x square twice. So when you differentiate x square once, you have 2x. When you differentiate 2x, then you have 2. So you are going to have 2 over 4. And then you multiply 1 over 2 across, so that you have 1 over 2 x square minus, this cancels out this, so you still have 1 over 2 x, and then 2 cancels out 2, so you are left with 1 over 4, so plus 1 over 4. So this is yp1. This is yp1. Now let's try to solve for yp2. So for yp2, we have 1 over d plus 2 also times e to the power negative 2x. Now we said that if you have yp equals 1 over f of d times g of x, where g of x is an exponential function, then basically we are going to substitute the value of a into the polynomial function of the d operator. So we are going to have 1 over, now we have this to be the polynomial function of the d operator, so, and then we have a to be negative 2. So we are going to have negative 2 plus 2 times e to the power negative 2x. Now you realize that this will not work because the denominator will go to 0. Now since the denominator will go to 0, then we are going to multiply the numerator by x, and then we have f prime of d. So we have d, or we have f of d to be d plus 2, then we have f prime of d. If you differentiate d plus 2, then you have 1, and then because 2 is a constant, it goes to 0. Therefore we have yp2 to be equal to, we have x over, this is 1 times e to the power negative 2x. So finally we have yp2 equals x times e to the power negative 2x. So this is yp2. Therefore we have yp to be equal to yp1 minus yp2. So that is 1 over 2 x square minus 1 over 2 x plus 1 over 4, and then minus x e to the power negative 2x. Therefore the general solution y is equal to yc plus yp, and then we have yc to be c1 e to the power negative 2x, and then plus yp, which is plus 1 over 2 x square minus 1 over 2 x plus 1 over 4, and then minus x times e to the power negative 2x. So that's it for today's video. Thanks for watching, and see you in my next video. Bye bye.